It's a great pleasure to be invited to give a talk for the conference. So first of all, I would like to thank the organizer of the conference. Today I'm going to talk about Einstein equation. So I feel very happy because I realized that this building is called astronomy and mathematics building. So Einstein equation, so let me give you a few terminology. The first one is Lorentzian manifold. So Lorentzian manifold is just a differentiable manifold equipped with Lorentzian metric. So Lorentzian metric has signature -1, +1, and +1. Here we have 1, -1, and n +1. So Riemannian metric, we have signature +1 and +1, +1. So what's this Lorentzian manifold used for? They are very useful. Because in general relativity, the space-time is described by a 4D Lorentzian manifold. And Einstein found that the metric must satisfy a so-called Einstein field equation. So let me introduce to you the Einstein equation. The equation is the following. R alpha beta minus R/2 G alpha beta plus lambda G alpha beta equals to kappa times T alpha beta. Here R alpha beta is just Ricci curvature, R the scalar curvature, and R alpha beta minus R/2 G alpha beta is so-called Einstein tensor. And lambda is so-called the cosmological constant. Kappa is just universal constant. Roughly it is A pi times universal gravitational constant. So T alpha beta is so-called energy momentum tensor caused by the matter or field distribution of the universe. So the left-hand side, just some quantity determined by the geometry of the manifold. The right-hand side just is the quantity determined by the physics. So the equation just looks like geometry equals physics. So this is the Einstein equation. I want to say that this equation in many concrete situations, this energy momentum tensor has very explicit expressions. For instance, in the presence of electromagnetic field F, this F, you can think of this just as a two form in the space-time. And the energy momentum tensor, T alpha beta, just R F alpha gamma, F beta delta, G gamma delta, minus 1/4 F squared times G alpha beta. The F must satisfy so-called Maxwell equation, dF equal to 0. So F is closed, and the D star F is 0. So it means the Hodge deal of F is also closed. So here the Hodge operator is defined with respect to the Lorentzian metric.
Where is that equation defined under constant for dimensional space?
For 3 + 1 Lorentzian manifold. So 4D, total 4D. Okay, so this is the Einstein equation. Second terminology I want to introduce to you is stationary solution. A solution to Einstein field equation is said to be stationary if it emits a time-like Killing field. X, it means that the lead derivative of the metric with respect to X is 0. And X is time-like, so it means the inner product of X with itself is negative. So there are various slightly different definitions, but I keep this one as the definition of stationary solutions. Stationary solutions are very useful. They are used to model positive time-independent states of cosmological system. So you can think of the evolution of Einstein equation. As time goes to infinity, then you can imagine that there will be some time independent limit states. So you can think of there is time some stationary solutions. Yeah, that is to say, it possibly means some killing field. There are a lot of examples of stationary solution. For example, the Schwarzschild solution. Yeah, Schwarzschild solution, Kerr solution, Reissner-Nordstrom, Kerr-Newman solution. All these solutions are so-called black hole solution. And I want to say almost all explicit examples we know actually are stationary. So stationary solutions are very important. Except for those solutions start with arbitrary Cauchy delta, that I think, except that one, then stationary solutions are important. So if the space-time has a parameter of one parameter family isometry, then the R orbits are time-like curves. So in this case, the infinitesimal generator of this action is a time-like killing field. So this automatically, so this is also in literature. Sometimes people call the existence of such R action called stationary. But this is our definition is slightly broader than this one. So here I make a few remarks. So understanding structure of singularity of space-time is one of the most important problems in GR. So, but by definition, there is no singularity in the space-time in the usual sense because we assume the manifold is smooth. So no singularity in the usual sense. But we have several ways to say the space-time have singularity. The one way is the space-time is not geodesic complete. Whatever you extend the space-time, if it is not complete, then you may say the space-time have some singularities. So the second way is the curvature tends to blowing up. So this is at boundary point. This is what we have in mind, the singularity, right? So another is the so-called cosmic censorship conjecture. So it says the following: no naked singularities in space-time. It means all singularities are hidden behind the black holes. So this is one most important conjectures in the structure of the singularity of the space-time. So if this conjecture is true, and we know the classification of black holes, then this will give you a full understanding of the singularities. So this is a very big picture of the singularity of space-time. So, but I will make some connection with my result and this conjecture. It'll be still it is very weak, but still sounds interesting. Okay. So this is one main result I will talk in this talk. So the M is a 4D geodesic complete stationary space-time. The Lorentzian metric satisfies the vacuum Einstein field equation. So here I assume the space-time is complete, and stationary. And the Einstein equation, vacuum, so there is no T here. But I require the cosmological constant is non-negative. Then this implies the space-time is flat. It's actually flat. So it is a quotient of Minkowski space-time.
Excuse me, does the positive cosmological constant mean expanding or contracting universe?
Expanding. Yeah. So I will talk about this point later. Expanding, not contracting. So when lambda is negative, in theorem A, the result does not hold. The example is very simple and canonical, just untitled theta spacetime. So this spacetime is complete. It's geodesic complete, but it's not flat. It's not flat. So let me talk about some previous results. I want to say that all previous work on the stationary solutions need to assume some chronological condition. Let me explain to you what is a chronological condition. Chronological condition says the space-time have no closed timeline curves. No closed timeline curves. So it means that you cannot travel from the future to the past. So you cannot. So no closed timeline curve. So this is a very reasonable physical condition. It is easy to see the space-time always locally chronological. Locally, space-time always chronological. But in the whole, we do not know actually. For instance, in a very big system, so big that our galaxy is one point in this model, we cannot say. I do not know actually whether this condition also hold or not. I do not know. So chronological is very important. This condition, it says it has a very important implication. So if we have global R action, then these two conditions together will imply the space-time has a reduction from 4D to 3D. In this case, the space-time is diffeomorphic to n cross R. N is orbit space. Because we have R action, so you have orbit space. It is a smooth Hausdorff manifold. R is just real line. And under this diffeomorphism or global coordinates, the Lorentz metric can be written in this simple way. U squared just the norm of the Killing field minus U squared. It's because it is negative. Theta is a one form. On N. Gn is a Riemannian metric on N. So these three guys, one function, one form, and one Riemannian metric on N. These three guys are time independent. So roughly speaking, if you have chronological condition and global R action, then you can work and you can just look at everything on a three-dimensional Riemannian manifold N. You can just work on this N. Sorry. So the first work is a result due to Lichtenowitz in 1955. It says the following. So if a space-time 4D space-time satisfy the following condition, one is geodesic complete. The second is vacuum Einstein equation. Vacuum. The third is chronological and the global R action. And the orbit space is a asymptotic flat 3 manifold. So several conditions. Then this implies the space-time is flat. So here, besides these two conditions, chronological and global action, he assumed the orbit space is asymptotic flat. This condition was removed by Mike Anderson in 2000. So so they just the theorem is look like this. Just so stationary, geodesic complete, vacuum Einstein equation, and the chronological, and the global action, and the space-time is flat. So Michael Anderson removed the symptotic flatness condition in Lignowitz result. So how about without this chronological condition? So what will happen if we do not have this chronological condition? So let's consider a simple example. We consider the Minkowski torus, T2. So this is a two-dimensional example. We equip T2 with a flat Lorentzian metric minus dx squared plus dy squared. So and you can take a almost arbitrary time-like Killing field X with irrational constant vector field. So this will gives you the following. Any orbit of X is dense. So you can think of this picture. So you have, here we have a torus. So let me just draw a picture. So this is a torus. Of course, it is not like this, just this one. But we just identify these two sides and these two sides together, then you get this torus. So irrational square. So you have an irrational constant vector field. Then the orbit, any orbit, just closed. So here, then you get here, then you get here, and then you get here. Yeah. So you can imagine that. No. It is dense. Any orbit of X is dense. So if I want to look at what happened for the quotient orbit space, the orbit space is very bad actually. If you equip the orbit space with quotient topology, the topology induced from T2, then it has only two open sets because any orbit is dense in this space, so we have only two open sets. One is empty set, the other is the whole space. So it is impossible to write equation on N and do estimates actually, because this space is very bad. So actually in Anderson's proof, he used the collapsing on this three-dimensional manifold N. So, but actually it is not necessary. I will show you in a moment. Not necessary. He asked in his paper that whether the chronological condition could be removed in his theorem. Of course, I removed this condition in the previous theorem. To formulate the local estimates in the next theorem, I have to introduce a Riemannian metric G hat. So this metric G hat defined in the space-time, but it is Riemannian, not a Lorentzian. It is defined in this way. G hat equals to the Lorentzian metric Gm minus 2 times this guy. Here X star is just the one form obtained from the vector field X by lowering indices using this metric. So this is just the dual of this one. So here, if in the Minkowski space-time, so this guy just the Euclidean metric. So this is a very simple and clear picture. So in Minkowski space-time, R31. So this GM just dx dt plus ds1 squared. So this g hat just dt squared plus. So this is the Riemannian metric. So this is a Lorentzian metric. So they associate to each other with this Killing field. Here the Killing field just this one. It is very interesting that for this Lorentzian metric G hat, this Killing field, this vector field still Killing field for this metric. You can prove it. It's not difficult. And we can actually relate the Riemannian geometry of this guy with the Lorentzian metric of this guy. So you can compare the geometric property of these two manifolds. So this is the idea so this is an important theorem for us. So it says the following: if the Lorentzian manifold is geodesic complete, if and only if the remaining manifold is geodesic complete. So I will use this in a moment. Okay, this is what I mentioned a moment ago, so-called local curvature estimate. I need this one to prove the theorem A. This is theorem A prime. So it states in the following: if the space-time satisfies the vacuum Einstein equation, so with the non-negative cosmological constant, and actually, I only need this condition holds on ball of radius A. Here, this is a ball of Riemannian metric with respect to Riemannian metric G hat metric. I assume this closure of this ball of radius A is compact, NAM. So this ball of Riemannian distance, geodesic distance A, with respect to this metric, Riemannian metric defined a moment ago, then the norm of the curvature on a slightly smaller ball, radius 1/2, A/2, is controlled by C times A to the power minus 2. A is the radius. Here, this curvature, Rm, is the curvature of the Lorentzian metric, Gm, Lorentzian metric. And the norm is defined with respect to the Riemannian metric. So combining the previous theorem, because I proved that MGM is complete, if and only if MG hat is geodesic complete. So if we assume that this equation holds a complete geodesic complete manifold, then I can take this A goes to infinity, then this will tends to 0 actually as A goes to infinity. So this tells you the curvature actually identical to 0. That is to say the space-time is flat. So this is the key estimate. Sorry. So I will give give a interpretation of this estimate. So this curvature estimate says if the Killing field never tends to become null. Null means the norm is 0. The norm is 0. Norm of the Killing field is 0 at that point. Then we have quantitative curvature estimate. It means space-time is regular. So this is just the following result. Of course, this is not regular. The boundary of largest inextendable stationary space-time consists of the Killing horizon. So this is not regular, but somehow it says this should be true. Should be true. Because our physical space-time is not flat, right? So it's not flat. So some condition theorem must be violated, not flat. So if we assume the space-time is stationary, and the vacuum, so the completeness condition must be violated. The condition of the theorem must be violated. So if you assume it is stationary and a vacuum, then completeness must be violated. More precisely, suppose we have a space-time curvature at a point, one point. For instance, here, 1 point. You have the curvature at this point has a norm r. Then you apply our local curvature estimate here. Local curvature estimate. This you get this inequality. R is the curvature at this point, at x. Sorry, this should be p, right? Should be p. So R is less than c times a minus 2. So this implies a less than square root of c times r to the power minus 1/2. So that is to say, a ball of radius. This ball is a geodesic ball with respect to this metric. Is not compact. Should be 2 times, in terms of my estimate, 2 times square root of c r. But c is a universal constant. So somehow I can safely say just c, some c times r to the power minus 1/2, not compact. This ball is not compact. So this gives you some information how far from the singularity. How far from singularity. It says this radius, above this radius, not compact. Not compact. Because we know in the theorem, in the Hawking and the Penrose singularity theorem, it says there is some singularity in the space-time, right? The result said there is some singularity. But the proof is argument by contradiction. Argument by contradiction. They assume the space-time has some trap surface, and some other geometric condition. Then it says under this condition, the space-time must have some singularity, or some geodesic must be incomplete. But because the argument is argument by contradiction, so we do not know how far the singularity will be. But here it is explicit. This C is just a universal constant. But of course, we assume the space-time is stationary and vacuum. This is special. This is a condition. But still, I think it is interesting because in many applications we assume the space-time not only stationary, it is static. Static. Okay. Let me talk about the proof. I will give a sketch of the proof. So the first, I will write the Einstein equation in terms of the Riemannian metric G hat. So Einstein equation is an equation on Lorentzian metric. Here, I write the equation in terms of G hat, this metric, and using a harmonic map argument in general relativity setting. This idea is not new. How, as we mentioned before, we this condition, this expression does not hold in the whole space-time. In general, we do not know whether it holds or not. But locally, this always holds. We can find the coordinate around a point so that the Lorentzian metric has this form. G is some space, some Riemannian metric, the space direction, and U is time independent, theta is time independent, G is time independent. And we consider omega. Omega is the star u to the power 3 times the star d theta. Star d theta. Omega is a one form actually. Omega is one form. So the vacuum Einstein equation implies this omega is closed. Omega closed. So locally, you can find another function psi. A function psi, so that omega equals to d psi. This is Poincare lemma. Poincare lemma. Sorry, I can just use this. So it is important to consider this metric G tilde. It equals to U squared. It is a conformal of the Riemannian metric. The G is just this one. G is here. G, this G. This three-dimensional. You can think of this three-dimensional Riemannian metric. So consider conformal change of this G using this norm of the Keeling field U squared. Then the Ricci curvature G tilde is just very simple. It is this expression involves the omega tensor omega plus d log u tensor d log u. So this is very simple. I want to say that if we consider the Ricci curvature of G, not the G tilde, then the Ricci curvature G will involve the second derivative of u. Second derivative of u. But if we conformally change this G to G tilde, then the second derivative will disappear. Only involve a first derivative of u and actually first derivative of the psi. Psi just this one. Psi this one. Psi this one. Okay, so we consider upper half plane actually. H, it is upper half plane. So just y is positive. So this is the metric. And we define a map psi x y. This x just the psi we defined before, and y equal to u squared from the manifold space time to H. We can show if this lambda is 0, the cosmological constant is 0, then the psi is a harmonic map actually, harmonic map. So this is a key point. From this Riemannian manifold M equated with Riemannian metric G hat I defined before to this space, upper half space. It is a harmonic map. So this is very important. Very important. So from this expression, you can see if I pull back this this metric using this map psi, then I get this one. So I get this. It is just the Ricci curvature of the conformal Riemannian metric, right? It's just the Ricci curvature. So we can compute the Laplacian of this psi. So this is the computation. So if this one is 0, here bar is the Ricci bar is just a metric for the Lorentzian metric. Ricci curvature of the Lorentzian metric. So if lambda equal to 0, then this is 0. So the hat the side, the map side. So maybe I use a different notation, right? Can you see? Yeah. I'm sorry for that. So this map is harmonic. So once we know this map is harmonic, then we can use standard Bochner formula, right? This is very standard here. This formula for the energy of a side. Energy of a side. E psi Laplace hat, and you get this term, and this term, and this term. And we mentioned that the E psi is the energy, the pullback of this side, pullback of the metric, just a Ricci curvature of the metric G tilde. So the trace, this E psi actually, it is somehow the scalar curvature, because you see this is non-negative, right? This is non-negative. So the metric of conformal metric, the Ricci curvature of the conformal metric is non-negative. Sorry, let me see. Where is this expression? Here. Yeah, this is non-negative. I forgot to tell you, this is non-negative. So this term, the energy actually controls the curvature of the metric G hat, the energy. And of course, not up to some function u, right? But u to the power u, not exactly the scalar curvature, not exactly scalar curvature. We have to multiply this quantity by u to the power 2, u squared. I think it should be this one.
So you repeat your feet involving metric in the domain and also metric in the power.
Yes. The energy of the map. Yeah, we defined using two metrics. So after a very long computation, I skipped all this. It should several pages to do this. It's very, very long. But finally, we can prove that the energy, the Laplace of this energy, equals to this several term. All these terms actually non-negative if we assume the space-time is flat, Ricci flat. So here this non-negative, also this one, on this one. And I2 is this one. So if Ricci flat, then this is gone. Actually, this is also gone. So all these terms are non-negative. Okay, so the proof now is very clear, right? So we can assume this A equals to 1. So the argument actually fall in two cases. The first case is the boundary of the ball of radius A is not empty. The second case is empty. This case is easier. We do not discuss here. So we only treat this case. In this case, so you can consider this H just the energy function, right? Somehow just the energy function. So you multiply this function H by some cutoff function actually. So if this is the distance to distance function to the boundary. So actually this is quite standard point picking technique, right? So since this f is non-negative and vanish in the boundary, so there is point in the interior so that the x bar at the maximum f is achieved in this point, in this point. So to prove the theorem, it suffices to prove there is a universal constant c, so that the value of f at this point is bounded by universal constant c, because this is scaling invariant quantity. So if you get this, then you immediately get the result. So How much time do I get? Okay, I still have time. Okay, so now we argue by contradiction. Suppose there are a sequence of space-time and the G hat L ball with compact closure, and this space-time satisfy Einstein field equation, vacuum Einstein field equation with non-negative cosmological constant. But the Fx bar L, this quantity goes to infinity as L goes to infinity. So this is these two points. So we work on a fixed space. So we drop the subscript L. So we make a scaling actually. So because we know this function scaling invariant on the metric, so you make some normalization. You can assume U at this point is 1. You can make a scaling, and H at this point is 1. H is 1. U is just this function. U is this function. H is this. Roughly, the H just as I tell you, the H just the scalar curvature of the G hat metric, the curvature of the G hat metric. So because this point X bar is almost the maximum point, so it controls the curvature, control the quantity, the multiplicity of the quantity in nearby points. So this you have this, but because H involves the gradient of U, so this holds. So U is controlled in large ball. Actually, I only need this ball, this radius D to be 1. Actually, not too large. You do not need that. And if this is controlled, then the curvature is controlled also for this G tilde metric. Actually, I just want to say this G tilde is only defined a very small neighborhood at each point, not a globally defined metric actually, not a manifold. No, there is no three-dimensional manifold to say that G tilde is a metric. It's just locally. This is computation local, but the curvature still makes sense. So now we consider an exponential map. Actually, this exponential map is the metric. You can take it to be the exponential map of this metric G bar, conformally changed by function U square, or this one. So this is not really the exponential map. It is defined only in the orthogonal complement of the Killing field at one point, at the point. X bar is the maximum point, this point. So you consider exponential map of this, for instance, this space-time metric, but only you restrict the exponential map on the orthogonal complement of the Killing field. So we claim that there is a universal constant, delta, so that this exponential map is an immersion from some ball of radius delta 1. The delta 1 is truly universal to B hat. B hat is the 4D manifold, but this ball is 3D Euclidean ball, 3D. So moreover, we can prove that the pullback of this one is strictly positive definite. So this claim is very useful. Because we can pull back this metric or tensor. Actually, you can think of it as just a tensor G tilde by this exponential map. Pull back everything to the ball of radius delta 1. And I mean here the function U, the one form, and everything to this ball. because this ball is contractible, the function C must satisfy this equation. We can find another psi because we only have omega. In the beginning, we have omega. Locally, we have psi. But here, because this ball is contractible, you can find a psi here, and a psi on this ball. So you pull back all these quantities and use same notation to denote them. Because we know that the curvature of this guy is bounded. It's bounded. Curvature of this guy is bounded. It is bounded. So we can construct harmonic coordinates with respect to this magnitude. This actually the pullback of some tensor, right? But if you pull back, then it becomes really a metric, a three-dimensional manifold. So you write everything in these harmonic coordinates and use the elliptic regularity for the function u and the one form the omega. Then you can prove that they are actually C infinity. They're smooth. And this will tells you if I take limit, then the maximum of this function in the energy can also be achieved at the origin because your convergence is C infinity. If your convergence is weak, then you cannot say. For each sequence, the maximum is 1, but if the convergence is weak, you cannot say the limit still has maximum at the origin. But here we have C infinity convergence. So the maximum 1 is achieved at the origin. Now we can apply the Strong-Mason principle for the limit. So we can use Strong-Mason principle to this equation. So this is the equation. If E attains the maximum at the origin 1, the maximum point at this one, but all these terms are non-negative. On the non-negative right-hand side, you apply Strong-Mason principle, then you get all this term has to be identical 0. For the first one, you get u equal to constant, right? So the nabla log u equal to 0, so u is constant. So u is as I mentioned before, u equal to 1 at the x bar. So here, u is identically 1. So for this term, because u is a constant, so this is 0. This 0 tells you omega is 0. Omega is 0. But it's impossible because if it's just omega squared times log u. So this 0 tells you if is 0, but it's impossible, right? Because we assume if is 1 at the origin. So this is a contradiction. Okay, so this is a proof. Actually, we can extend our theorem to. We can allow our equation to include include other matter fields. For instance, we can include the electromagnetic field. Here is F, the electromagnetic field. Lambda is still non-negative, but kappa is negative, kappa non-positive. F satisfies the Maxwell equation, and the Lie derivative of F is 0. Here I said inheriting means this the electromagnetic field inherits the symmetry from the space-time. Inherits. So this is inheriting. It is not necessary to satisfy this equation. If you only assume space-time is stationary, and you have this equation, it is not necessary. This should be true. Not necessary. But here, I assume inheriting this metric. So the important condition here is this one. So I have to assume the Poynting vector vanishes. The Poynting vector is just the wedge of the electric field and the magnetic field. These two guys are one form, actually. One form. So E wedge B is just the Poynting vector in physics. Poynting vector. I assume this Poynting vector vanishes, then space-time is still flat. And I can also generalize this to include some scalar fields. Scalar fields. Here is phi satisfy so-called Klein-Golden equation. Klein-Golden equation. This is so-called Klein-Golden equation. This Laplace is the Laplace defined by using the Lorentzian metric. This m is the mass, and h bar is the reduced Planck constant. Actually, it is the Planck constant divided by 2 pi, reduced constant. This is positive, and I assume this is Poynting vector vanishes, then still flat. Okay. So I can also have local curvature estimate for Einstein-Maxwell equation for the previous the theorem. Here I do not need to assume the Poynting vector vanish. I assume it is bounded in a invariant scaling invariant way. So the Poynting vector is bounded, it is controlled, then the curvature is controlled. So for inheriting Einstein-Maxwell-scalar equation, I can get this estimate. But still, I need the boundedness of the Poynting vector, but I get this estimate. Here, the estimate says the following: for any delta, there is a constant c delta depending only on this delta and the dimension. There's only dimension 4 here, and we can control the normal, the curvature in terms of the mass of the scalar field and some constant times this one. So if we assume the space-time is complete, then we can take this a goes to infinity, then this term gone. This term is gone, right? So you can take this term is go to 0, then you get this one. Then take delta equal to 0, and you get this one. So this is the estimate for Einstein-Maxwell-scalar field, scalar equation. So proof is the idea is similar, but the computation is complicated. It is complicated. So we have to consider this quantity here. We have to consider 2 more quantities: electromagnetic field and electric field and the magnetic field. This condition, Poynting vector vanishing, imply this omega close. Why we need this condition? The condition is just used here. Poynting vector vanishing imply this omega close. It's very important. These 2 guys are closed always. 2 guys are closed. So then you compute. You consider a Riemannian manifold here. Then this metric. Define a map, define a similar map, involve all 4 quantities. The U, psi 3, psi 4 is the potential of the electric and magnetic field. Then this guy is still harmonic, so you have to do a lot of computation to say that this guy is still harmonic. And you use Bochner type formula, then a lot of computation. Yeah. All of these terms are non-negative on the right-hand side, non-negative. If we assume the lambda is non-negative, kappa is negative, kappa non-positive, and the kappa prime is non-negative. So we still have high dimensional case, but here high dimensional we have to assume the space-time is static, stationary. Somehow too difficult. I think stationary should not be true, stationary, but static is we can do. So let me give one final explanation why the theorem should be true. So I maybe give you one command to your question. So in the computational model of general relativity, this lambda, cosmological constant, positive means dark energy. this kappa non-positive and kappa prime positive will cause acceleration of the universe in the model. This quantity, the sum of these quantities will cause acceleration of the universe. So intuitively, this will reduce the matter or the energy density distribution of the universe. So it makes space-time more regular. So this is one explanation I have in mind. But otherwise, I do not know why this should be true and not the converse. Right? So maybe I stop here.
So, I mean, because in Hawk is the singular series, right? We assume that some kind of weak energy condition.
Yes. Yes.
So, do you think that that can be applied to the case? To prove that incomplete?
Yeah, maybe not, because I need an equation. Yeah, Einstein field equation, but their condition is dominant energy condition or something like that. But their assumption is stronger because they have to assume the existence of trap surface. The existence of trap surface is not so. Yeah, this is a difficult question, right? Difficult in terms of work of Cristolo. Existence of trap surface is difficult, somehow equivalent to the existence of black holes. But here I just assume the equation is good. It is satisfying vacuum Einstein equation. But what most important, I have to assume the space-time is stationary. So this is most important assumption, I think, stationary.
So what happens if quantum vector is not zero?
Yeah, actually, if the point vector is not zero, we can still get estimates in terms of norm, the quantity of the point vector. So I state this. So
But it's not flat.
not flat, but it controls. Yeah, the estimate says the point vector controls the everything, controls the norm of the curvature, point vector. I don't understand. I don't know physics actually. I don't know.
And then for the standard field, there's also an energy flux.